Hi, Mr. Pre-Calc, welcome back. This is the Hilvert Rutherford Notes Session 2. This is Mr. Rutherford. And today we're going to be using parametric equations to solve real-world application problems. And we're going to be talking about horizontal and vertical motion today. So first of all, let's make sure you got your calculators out, ready to go. We're going to be doing a lot with your calculator. And you want to make sure that your calculator, if you recall from our unit we had before, that you are in parametric mode. And on the calculator, if you hit mode, you're going to see that as PAR, like so, next to function and next to polar. So select that parametric, and let's go ahead and dive into this first problem. So it says Ben can sprint at the rate of 29 feet per second. Jerry sprints at 23 feet per second. Ben gives Jerry a 12-foot head start. The parametric equations can be used to model a race. So here we have Ben, we have x sub 1 is equal to 29t, so that 29, of course, is just the speed. And then remember that Jerry is given a 12-foot head start. So you're going to see this 12 right here, that's the head start. And then 23, of course, is Jerry's speed. And so what you're going to do is you're going to go into your y equals once you're in the parametric mode, and you're going to type your x sub 1 as the 29t. And remember, to access the t, you just hit the button you normally would hit, the x, when you're in function mode. When you're typing in a normal linear equation or quadratic or something and you want to type in x, you've got that button right below the mode button, which is x, t, and then you see theta and then n. So once you're in parametric mode and you type that button, you're going to get the t. It'll be a capital T, but you'll get the t. Then these two values here, these are pretty arbitrary. We're just going to set them as 3 and 5 for this notes, but these can be, these values, y sub 1 and y sub 2, separate the two lines. So when you end up graphing it, you have to have these different. They just have to be different. It doesn't matter what they are. You don't want to go too big or too small because you're just going to have to change your window, but they'll be pretty far away from each other. But they just have to be different. They could be 4 and 5. 3 and 5 gives them a little bit of space, but they just have to be different. So just don't do the same thing. That's all. Okay, so once you've got them in to your graph, you can, and we're going to go ahead and use this window here. So set your viewing window. So you're going to have your t 0 to 10. So that's just like 0 to 10 seconds. We'll go our steps at 0.05 for the t's. The x min, remember this is an interval notation, so 0 to 200. And then our y will be -1 to 10. And that's just in response to these numbers that we have up above. So if we went from 3 here to 5, so -1 to 10 gives us space above and below to give it some context. Okay, so once you've done that, you should get a window that basically looks like this. I'm just going to draw a quick sketch. So you have here the this line down here where y is equal to 3. It actually touches right there. This is going to be the line that's Ben. And then you're going to have one up above, which starts out here a little ways. And this is going to be Jerry. And the reason it starts out, remember, he was given this head start. So this little distance from here to here, that's going to be that extra 12 feet, okay? So it says, who was ahead after 1 second? So what we can do is, going onto our calculator, we can hit second, and then trace, which is really the calculate button. And then you can type in t equal to 1. And then what you can do is you can use your arrows on the calculator to jump from curve 1 to curve 2. So that's going to help you kind of go back and forth. And so what you're going to find is that as I press that in, so I'm going to do the same thing with you. So I'm going to hit 1 on here. And on the first curve, I'm going to find out that I'm right here when t is equal to 1, it says that x is equal to 29. As I hit the up arrow, you'll notice that it kind of jumps a little bit to the right, and it has a 35. So what this means is that Jerry is ahead, and I'll just say is ahead by 6 feet, because Ben is at 29 feet, and Jerry is over here at 35 feet. Okay, so let's take a look at the next question. It says if they are running a 150-foot race, who would win? Now you can use the trace function on your calculator if you'd like. I'm going to choose to do this algebraically as opposed to graphically, but really it's up to you what you want to do there. So let's start with Ben. I'm going to write 150 is equal to 29t. I'm just going to divide those two, and I end up getting t is equal to 5.2 seconds. And then let's go ahead and take a look at Jerry. So we've got Jerry, and we're going to write 150 is equal to his equation, which is 23t plus 12. Subtract the 12, divide by 23, we get t equals 6, and that would be seconds. So as you can see with that, you've got 5.2 seconds, so that's less time, right? So then 6 seconds, so 0.8 seconds difference. So we would be saying here that Ben would be the winner because he's getting to that 150-foot mark faster. All right, let's take a look. Maybe some of you have seen this show from maybe the 1970s, before my time, but there's a movie called Starsky and Hutch, so here we have a reference to that. Check it out as you have some extra free time. It's a good movie. But Starsky and Hutch are two opposing players, and capture the flag are 80 feet apart. Now, before we get into all this, just kind of think about what would be happening here. You've got, let's say we've got Starsky over here, Hutch over here. Here's our flag in the middle. So they're 80 feet apart total. That means that they are how far from the flag? Well, of course, that would be 40, right? It says it in the problem, but just kind of to keep that in mind. So we've got these guys running towards the flag to grab it. On a signal, they run to capture a flag that is on the ground, midway between them, like we said, at 40 feet. Starsky is the faster runner and runs at a speed of 10 feet per second. However, he hesitates for 0.2 seconds. Hutch runs at a speed of 9 feet per second. And so we would assume that he doesn't hesitate. The following parametric equations model the race to the flag. So here we have Starsky. We got the 10, which is the 10 feet per second, but here's the hesitation. He's behind because he starts 0.2 seconds after Hutch. And here we have Hutch. And what you want to think about is the reason you have a negative here is because they're running in opposite directions. You've got Hutch who's running to the left, and we've got Starsky who's running to the right, or you could have it vice versa. It wouldn't really make any difference. But they've given us the equations, so we're just going to use those as we have them. And the 80, of course, is in terms of the 80 feet they are apart. And then there is this 3 and 5 again. Just again, it doesn't matter what they are. Just make sure they're different so you can separate the lines. That's all. Okay. So we want to set our viewing window. So you'll notice that this is pretty similar to the last viewing window that we had in the last problem. The one difference is the x, which is an interval of 0 to 100. I think last time it was 0 to 200 maybe. So what we can do is we can trace along the graph to answer the question. So what we want to do is answer who captures the flag and by how many feet. Okay, so what I'm going to do is I'm just going to draw a quick little diagram of when I graphed it, kind of what it looks like and what you should be seeing. Okay, so we've got here Starsky, which I'll kind of go this direction. Okay, so he's running to the right, we'll say. And we've got Hutch, who's running here to the left like so. And let me go ahead and label those. So here's Hutch, and here's Starsky. Okay, so what we want to figure out is who can make it that 40 feet first. So let's just do a little bit of algebraic work here so you can kind of see what's going on here. So I'm going to have 40 equal to 10 times t minus 0.2. And again, this is for Starsky. And I'm going to solve that for t. And what I end up getting when I solve that, I get t is equal to 4.2 seconds. In other words, it takes Starsky 4.2 seconds to make it 40 feet. Okay, so here's Starsky, starts here, and after 4.2 seconds, boom, there's 40 feet. All right, so I'll just put a 40 right there. Okay, so now let's take a look at what Hutch is doing. So for Hutch, we've got the 40, and that's going to be equal to 80 minus 9t. And we end up solving that, and we get t equals 4.4. Now, when you're at 4.4, you'll notice that when you graph it, it ends up putting him right there. Now, it labels this as 42.4 because we're talking about a distance from this point, which we'll call the origin. So from here to here, that's 40. And we go a little further, and that would be 2.4, which is 42.4. But remember, Hutch is racing this direction. So in reality, he hasn't really run 42.4 feet. You have to subtract off the 2.4 from 40. So if you do that, he's really, running 37.6 feet, and you've got Starsky who's run the 40. So what we would say then is that Starsky is going to be the one because it takes him less time, to run that 40 feet, 4.2 seconds. So Starsky is going to capture the flag, and he captures it 2.4, or do we say 2.4? Is that right? I think I maybe wrote the wrong 2.2, I think it was 37.8. My apologies there. Let me go back here. I was writing down the notes that I had, that a work I did earlier. This is actually an 8, and this would be 42.2. So that's a 2.2. Okay, so let's take a look here. So this is actually going to be 2.2 feet ahead of Hutch. So he wins by 2.2 feet, or you can see here, you had that 4.4. We might even just say 4.44. If you divide it, it's actually 4.4 repeating. But so, he's ahead by about 0.2 or 0.24 seconds, or 2.2 feet earlier. Okay, so let's go ahead and move on to the next problem here. And just kind of keep in mind what we just worked on. And so here we have a scenario, and we need to find the equation. So in the last couple of examples, we were given the equation. So fourth graders Emily and Molly are on the playground about to have a race. So almost identical to Starsky and Hutch, but we're not running after a flag. When their friend yells, "Go," Emily hesitates for 0.5 seconds, or half a second before running. Write two equations that show Emily and Molly tying after 5 seconds, and Emily winning the race. Check your equations with a calculator and fill in the window. Okay, now, this is a little arbitrary. We need to, first of all, let's set how fast Emily is going, and that really can be any number. It doesn't really make any difference. We could say she's running 5 feet per second, 10 feet per second, 20 feet per second. I'm going to go ahead and do 10 feet per second. So for her, we're going to have 10. But then remember, she was hesitating. So we're going to write t minus 0.5. Now, it says after 5 seconds, they're going to need to be at the same exact spot. So we need to figure out how fast Molly is actually running. Now, I figured this out earlier, so I'm just going to go ahead and give you the answer, but I'll show you how I figured it out. So if you have 5 seconds, in other words, if we were to plug in 5 right here, then 5 right here, and we were to set these two equal to each other, again, assuming I don't know the 9 yet, I would end up solving and finding that Molly's running at 9 feet per second. So that's where that 9 comes from. Okay, so again, if I was to take the 10, plug in 5, because again, we're talking 5 seconds here, minus the 0.5 hesitation equals to, I'll just say x, because I don't know some variable. It could be anything. You could put s for speed or something like that. And then this t here is actually also going to be 5. So I'll go ahead and erase that and put times 5. And if we solve that, we end up getting an x equal to 9. That's where that 9 is coming from. If I had chosen a different number other than 10 and chose 12, for instance, you would get a different value than 9. So it doesn't really matter how fast they're running. You just need to pick something for the first one and then respond accordingly. So I picked the 10 just like with the Starsky and Hutch model, and that ended up working out to be a 9 there. Okay, so what we're going to do here for the window, we're going to go kind of like what we did earlier. We'll go 0, let's say, to 15. So 0 seconds to 15 seconds seems reasonable. If we had a longer race, obviously we could do that, but we're talking about being at the same spot in 5 seconds. I doubt this is going to go much longer than that because Emily's caught up to Molly. And then we could just do a t-step of every half a second, 0.5, and you can make it smaller if you want. It's up to you. Don't make it too big though. We've talked about that before. Then let's go 0 to 200. This is just how far, we're going. So you can go pretty far pretty quickly. And then let's go ahead and go 0 to 7. We can go 0 to 10. I'm just going to go ahead and fill in 3 to 5 again, just like we did before. Okay, so again, these are arbitrary. They just need to be different. And they can be whatever you want. Okay, so there's an example of just kind of coming up with the parametric equations. So now those were horizontal movements. We're going to talk a little bit about vertical motion here in 2 examples. So it says a particle, and when it says a particle, because this could be any object, a baseball. It could be, a snowflake. I mean, who knows, right? Something dropping out of the sky. A particle is moving along the y-axis. Okay, so let's go ahead and draw that. So here we have our xy axes, and I'll just put the particle right here. It's moving this direction. It's given, the position is given by 3t plus 4. That would just be the height. It says set your viewing window. Okay, so let's go ahead and get our viewing window to 0 to 10. So you're going to go into your window, 0.05 for your t-step. X is -5 to 5, and then you have y is 0 to 35. So it says, what will the equation be for x of t? Well, remember that we've got something that's traveling along the y-axis. So here's our y-axis here. Well, when you're talking about that equation, remember that's a vertical line. That's going to be x equals 0. So we've got x of t is equal to 0 because, again, it's traveling along the y-axis. It says find the particle's distance from the origin after 5 seconds. So here we have the origin. So in other words, how high is it is the question. So what we're going to do is we're going to plug in 5. So 3 times 5 plus 4, and that's going to give us 19. So this is going to be above the origin. So it's 19 units, I'll say, above origin. Again, we're kind of assuming that the origin would be the ground, right? So it'd probably be above, we would assume. Okay, let's take a look at one more example. We'll be all set with those notes. You can pause it at any time. I apologize for my handwriting. Again, I'm using my finger here on my laptop, so it's not ideal. But so it says a particle is moving along the line x equals 4. Okay, so let's go ahead and draw that. So I'm just going to, since it's x equals 4, I'm just going to go like this here. And let's just say that's x equals 4. We've got some particle, let's just put it right there. It says it's moving along this. Now, again, it could be moving up or down, right? Because you could throw something up or throw something down. We're not really sure what it's doing necessarily, if it's falling out of the sky or what it's doing. But it says that its position is given by the equation f of t is t to the third minus 12t squared plus 36t. Okay, that's a cubic. So one thing that I think is helpful in a situation like this is to go ahead and draw that in rectangular form. So you can switch now, if you'd like, briefly to rectangular form, or you can just kind of follow along with what I've got. And if you were to do this in rectangular form, this is the quadratic t to the third, but it's going to be x to the third, of course, minus 12t squared plus 36t. But again, you'd have to put an x. But that's what that curve is going to look like. Now, what that sort of tells me is that the motion of this parametric situation is this is going to be kind of going up and then down. So here's the path of the ball: up, down, and then back up. So when you are in parametric mode and you start doing the tracing, what you're going to notice is that this dot or this trace is going to start coming down. It's going to come back up and kind of come back down. It does kind of some funky things. That is in response to what it's doing here, okay? So it says, find the time when the particle changes direction. That's exactly what I was talking about, where we have this up movement. So we're looking for the maximum. We can do this in the parametric mode or the function mode. It doesn't make any difference. I think it's a little easier in function mode to see it, though. So when we find that maximum, using the second trace on the calculator, we end up getting a point which is 232. Then if we were to come down here and look at, okay, it's coming down here to this minimum. This point here is 6, 0. Now, these points are actually on this parametric. So I'm going to label this one here. This is the 232, and then right down here is the 6, 0. Remember, it said it's moving along this x equals 4, so you can't see this sort of three-dimensionality to it. It looks two-dimensional. So it's moving this way and then back up this way. So you have the same points there. So what we're going to say is that the particle changed directions at t equals 2 seconds, and this is at a maximum, or we should say a relative maximum, localized maximum, and the y is equal to 32. And we're not exactly sure what units these are, 32 feet or what exactly it is. And then we also have at t equals 6 seconds, we have a minimum, and that's when the y is equal to 0. So now, and I should have said this earlier, when you're graphing this in the parametric situation, my apologies, you're going to have x sub 1 equals 4, and then you're going to have the y sub 1, let me write it right here, is equal to this t to the third minus 12t squared plus 36t. Sorry, I'm kind of running over here to the side, but that's what you're going to plug in. So you can eliminate the x sub 2, y sub 2, those are gone. We're just implementing those. That's how you're going to get this graph along with this window here. Okay, so maybe go back if you're wondering how in the world am I getting this picture. I'm sure you got the function part, but here, but maybe you had some trouble with the other one. So maybe go back and put those in, and then you can kind of see where I'm getting those numbers from, and if you need to pause, pause. So then it says find the total distance traveled in the first 10 seconds. Okay, so we can do that again on the parametric mode, over here, or we can do that here on the function mode. It's up to you. So when you're going from 0 to 2 seconds, you can see that the distance traveled is 32, and it could be feet or miles, or we don't really know, but or inches or something, but that would be from here all the way to here, That's 32 up. Then it travels another 32 from 2 to 6. So from 2 to 6, the distance is also 32. And then it says up to 10. So what you're going to need to do is, again, on the parametric mode or on the function mode, it's up to you. You're going to type in a value of 10. So we're going from 6 to 10. And what you end up getting is a point which would be like way up here, actually a lot farther than that up. Just for the sake of this picture, I can't get it any higher because it'll go off into the other one. Or it could be like way up here, right? When you get the 10, you end up getting 160. Okay, so I'm going to say that the distance there, we're going from this 0 up to 160. Well, that's going to be a distance of 160. So then what I need to do is just basically add these numbers together. And when you do that, you get a total distance of 224 units. Just going 32 and 32, 64, plus 160 is 224. So that's how much distance this object is covering as it goes up and down and then back up. But that's just between 0 and 10 seconds. It looks like that's going to keep on going, but we're just measuring it between those two values. Hope this goes really great for you. So take a look at the homework that's posted, work on those. We're going to have the keys posted to those homeworks as well, so you can be working on that. And yeah, I hope you guys have a wonderful, wonderful day. And again, let us know if you have any questions, either through remind texting, email, and Mrs. Hilvert and I will be happy to help. All right, talk to you soon. Bye-bye.